Oh, welcome everyone. Sorry about that. There was a tech issue. For some reason, I could not see all of you. I had only two students in the other Zoom session, and for some reason, I couldn't understand why. So I had to log off and then let everybody in again. I hope you can hear me. Can you hear me, please? Just want to make sure that we are all on the same page before we get started. Can you hear me?
Hi, yeah, I can hear you, but it only seems like it's just you and me, so it's just still only two participants.
Oh, okay. Let me see what could be. I thought let me see if I can. I thought I let everybody in. Let's
Yeah,
see if I have. It look like I have 13 students on the Zoom. Let me just see if I can. All right, everybody's coming in now. Come on in, come on in, come on in. I see everybody coming in now. There was a tech issue. I apologize for that. I don't know what happened. I see Adams, I see Angela, I see Bailey, I see Chris, Danielle. All right, Danielle, Chris. Welcome. Sorry about that. There was a tech issue. For some reason, I opened the Zoom session and I had only two students. I was waiting for more folks to come in until I received two emails stating that, if there was a lab today. Yes, we have lab today, and I hope we are all on the same page now. Let me mute everybody. I hope you can hear me. I see Nicholas, you have just unmuted yourself. And look, you just muted yourself. Let me mute everybody. You can use the chat feature if you want to ask a question. First, unlike the last two experiments where I had to record myself, today I decided to just be available in case you have a question. But if you are comfortable with a pre-recorded or pre-lab lecture, I can do that as well so that you can work at your own pace. Hopefully everybody has his or her lab kit by now. If you don't have the lab kit, please email me. Once again, I know Angelina, you emailed me and you are expecting your chem kit to arrive. I'll extend the due dates for those who have not received their lab kit. Uh, Having said that, hopefully by midnight you will turn in all those previous lab experiment. Today, our experiment is on collocative properties, and it falls under the chapter in the lecture solution. All right, and solution is made up of two things. Let me share my screen here so that I can be writing some notes for you to understand what the solution is. Here is my whiteboard. I'm just gonna use the whiteboard here, show you what a solution is. Solution is made up of two things. Solution is made up of what we call the solute plus the solvent. Plus the solvent. It's very easy to remember this equation. You should be able to take it further down to differentiating between the two. This is solute. Here is the minor what? Solute. This is the minor component. All right, component of a solution, and then solvent is the major component in a solution. When I took this code a couple of years ago, you know, I used to get confused because all of them start with SS, and you know, given in an exam, how will I know which one is which unless you write down the definition, how you identify, then you will know the definition of a solution. It might be in terms of grams, it might be in terms of moles, all right? That's how you look at the solute versus solvent in a solution. And it's not necessarily that a solution is made up of two substances. I know you may think that it could be only sodium chloride and H2O. No, it could be even two or more components, all right? If you have 4 components, the major one is the solvent, the rest will be the solute. Quite often we may think also that a solvent must be in liquid form. No, we can have a solution of solid. That means you dissolve a solid in a solid. For example, an alloy, all right, such as steel, such as sterling silver, such as bronze, all right. All those are examples of solid. That means you dissolve solid. In a solid, it does not form a chemical bond, but it forms an homogeneous mixture. We can also have a liquid, for example, or alcohol and water, they blend into one another. We say they are miscible. Air is an example of an homogeneous solution as well. That's just to give you an example of what solution is. You need to know that. Having said that, you know, I don't want to get into the intermolecular kind of, you know, how it forms, but I just want to really dive into properties of solution, which depends on the amount of dissolved particles in a solution. And those properties are called colligative properties of solution. Colligative properties of solution. These are solution, all right? These are solution which these are properties of, should be properties of solution which depends, all right, depends on the number of dissolved particles, all right, in a solution. So when you dissolve an ionic compound, for example, the solution will behave in a certain way, all right? When you dissolve certain compounds in a solvent, the resulting solution have some properties. These colligative properties right here, we have, or you should learn, understand, combine to your memory those 4 properties. I'll just give you, for the sake of the lecture, if you're taking the lecture right now, all right, these are the properties. One is the lowering of vapor pressure, lowering of vapor pressure. That means the vapor pressure of a solution will be lower than the vapor pressure of the pure solvent. And there is an equation for that. I don't want to get into details for that. There is an equation for that. 2, boiling point, there is boiling point, elevation. When you elevate, elevation, all right? When you elevate something, that means you raise. When you elevate, that means you raise the boiling point of the solvent upon dissolving a solute in, and it depends on how many particles are in there. The boiling point of the solution is always higher than the boiling point of the pure solvent, all right? And the change in boiling point, all right? Change in boiling point for pure solvent and the solution is given by this equation, you know, from previous chemistry course you took. Delta means change. This means change in boiling point. All right, change in boiling point. Subscript P for boiling point is given by, some of you may know this, we call Van der Hoef factor times what we call molar boiling point times molality. MA stand for molality. Let me break down this so that you know what it means. This means this means change in what? Change in boiling point of solution. All right, solution and solvent, of which, if we know the solution will have higher boiling point, this will be the boiling point of what? Boiling point of solution minus boiling point of solvent. Solvent. This is solution. Solution minus the solvent. Solution minus the solvent. That's how to get the numerical value for change in boiling point. Now, we call this Van Hoef factor, and it indicates the number of dissolved particles. This is the number of dissolved particles. You may look at it in forms of ions. You know ionic compounds. I know you know how to recognize where the ions come from the chemical formula for ionic compound. Let's look, for example, how to determine I. If we take, for example, sodium chloride as a solute dissolving in H2O, what is I? All right, I is what? You look at how many ions are produced. I equals to 2. In this case, 2 particles are produced for every one, formula unit of sodium chloride, for every one formula of sodium chloride. If I pick another compound, such as, for example, magnesium, all right, magnesium phosphate. This is the chemical formula for magnesium phosphate. This means we have 3 magnesiums, all right, 3 Mg, all right, 2 ions, and 4, not 4, but 2 2 phosphate ions, all right, 2 phosphate ions, and 5 particles. I equals to 5. That is how you look at the Van Hoef factor in this equation, right here. I just wanted to show you what this I stand for. How do you determine the I? And then P is called molar boiling point. Here, Kp, and you will be given this. This is called molar boiling point constant, and it is constant for every, all right, for every solvent. You will be given a problem molar boiling point for every solvent, and you have to just plug it in the equation, all right, and molar boiling point constant, and it's given in degrees per molar. And M, this is italic M, stand for molality. It is different from molarity, you know, from the Chem 1 and Introduction to Chemistry. Molarity is given by number of moles of volume in liters of solution. That is a unit for expressing concentration of a solution. Now, molality is a unit, or is a unit for expressing the concentration of a solution, and it's given by the number of moles, all right, number of moles of volume not volume, but mass should be mass in what? Mass in kg of solvent, all right? Solvent, and having explained what solvent is, you should know what it is, all right? You should know what it is, solvent. So you got to find the number of moles, of which the top part, all right, remember, number of moles is given by the mass which you will weigh, all right, over the molar mass of your solvent, molar mass of solute, all right. So you can use the chemical formula to find the molar mass. This is from the what? From periodic table, from the periodic table. This one you will weigh this, and then get the number of what? The number of grams of a molar mass give you the number of moles. And if you change the mass now, mass of the solvent to kg divided 2, you will end up with molality. You will end up with molality. This, plugging in this equation right here, will give you the change in boiling point of pure solvent and the solution of that solvent, solution for that solvent. I was just giving you that so that you understand how or what those terms mean. What is now relevant to what we are doing today is, this is number 3, collocative number 3 is freezing point what? This is freezing point depression. Depression is to lower it, bring it down, depression, to cool down, which means the freezing point of solution is always lower than the freezing point of what? Of the pure solvent. This is where the sodium chloride is added to, or is added on the roads up north, all right? If you have been to up north during winter time, they put salt on the road as sodium chloride so that the roads does not freeze. Why? Because it will lower the freezing point of H2O, bring it down to maybe -5. If the temperatures are in -2, lowering it to -5, the roads will remain clear of any frozen ice. So for this, the equation is the same as the boiling point. This is what we're gonna use. You'll use in this experiment, change in freezing point between the pure solvent, all right, and the solution is given by, it's the same thing, I, which is Van der Waals factor, number of particles dissolved, times the molar freezing point of the solvent. You'll be given that, times the molality. Molality is still the same as the one we looked before. And right here, let's look at the left side of the equation, Since, to end up with a positive number, since the freezing point of pure solvent is always higher, delta TF is given by freezing point of the pure solvent minus freezing point, all right, freezing point of solution. This will give you a positive value. This should be solution. For those who will watch later on, they might wonder what is that? Solution. This will give you a positive value. We want to make the left side of the equation here positive. And if the freezing point of pure solvent is always higher, we subtracted smaller value from the higher value. I is Van der Hoff factor. So if I have sodium carbonate, for example, if this one dissolved in H2O, I will be 2 for sodiums and plus 1 for carbonate ion, and I'll have 3. This will be, just giving you an example, this will be my I here will be 3. Molar freezing point constant here, it is specific for or unique for each solvent. You'll be given that. You'll be given that for each solvent. Now, molality, all right. Molality is the number of moles of mass in kg of the solvent, mass in kg of the solvent. So, the objective of this experiment, having worked to that, or before I walk you through an example, if you notice the example I've been giving you here, they are ionic compounds. Ionic compounds, you have to see the ion, the cation and the anion. You know what? Subscript, how to read the subscript, how to interpret the ionic compound, all right? So if I have iron 3 hydroxide, for example, iron 3 hydroxide, this will be 1 ion plus 3 hydroxide, this will be 4. I equals to 4 in this case. You got to see the chemical formula. This is for what? For ionic compounds. How about molecular compounds? Molecular compounds, all right, which are non-electrolytes. All right, these are non-electrolytes. That means they do not do what? They do not ionize. They do not produce ions when dissolved in H2O, for example. Sugar, all right, glucose, they don't form ions. That's why they don't conduct electricity. We read the background talk about the ions. So if I have this right here, I is always one for molecular compounds. Your compounds, to give you a heads up, the compound you'll be working today is I equals to 1. I equals to 1. You will read the background. It will tell you the composition of the solution you will make. The one with major component will be the solvent, which is the lauric acid. Benzoic acid, all right, I equals to 1 for benzoic acid. I equals to 1. So know what value will be for your benzoic acid, which is the solvent. I mean, which is the solute, what will be dissolved in benzoic acid. So here, lauric acid. This is the solvent. And benzoic benzoic acid is the solute minor component. So I equals to 1. I equals to 1 for molecular compounds. So how are we going to find the molar mass of a compounds? Given that, so in this equation right here, we know we can find this. I will be 1. You'll be given the molar boiling point constant for lauric acid. You have the molar freezing point for lauric acid. We will manipulate this equation in such a way that we end up with the number of moles. Remember, the objective is to find the number of molar mass. Let me show you how. The objective of this lab is to find the molar mass, all right, molar mass of molar mass of benzoic acid and determine the percent error from the literature of benzoic acid and find the percent error. How do we find the molar mass? The molar mass is given by the number of moles over, not the number of moles, but sorry here, it's given by, molar mass is given by the mass, right here, mass in grams over number of moles, You know that, units for molar mass is given by grams per what? Per mole. That is why we are using this equation, mass over number of moles. Now, at the top part here, this is from what you will measure out. What you will measure is the top part. This is from weighing. Weigh this. This is what you will weigh. That is what you will mass out from the, using the balance. All right. That is what you will weigh out. Let me see. Yeah, this is the balance you should have. This is what you will use to weigh your sample. Now, the lower part right here, from colligative property, which is what? Which is freezing point depression. I'll walk you through on how to navigate. This one you will get this, but what is the denominator? How will we rearrange the equation to get the number of moles? Well, you will weigh out, based on the procedure, you will weigh out the mass of your what? You better know the mass of your solvent. This is the lauric acid. You better know the mass by reading the direction, mass of the solvent. And bring the water to around 8, the direction called for 80. You can use anything, maybe your hot pot to bring the water to 80. And using the test tube, try to get as much as you can your solvent all the way to the bottom. Please don't weigh and then you lose during the transfer, even a crystal. Try to get everything at the bottom. If something gets stuck on the wall of the test tube, try to melt later on using the H2 and be careful so that, you will, and you should have a thermometer. I think it's talk about thermometer. You will record the mass after every, let's see, right here, show you, she'll be on the data sheet. This is what I wanted to show you, the data sheet. So if I have the lauric acid right here, the mass, all right, the mass is given, but you will have to record the temperature once it gets to 60. If you take the temperature to 80, it will take some time to bring the solution to 80. So if I bring my water to 70 instead of 80, the point is you should record the temperature at, all right, you should record the temperature after every 1 minute after 30 seconds, So you see here, 30 seconds. So if I have the temperature 60, 30 seconds, 1 minute all the way, you see the minutes here. So what I'll recommend is the direction call for taking the water to 8. If you have around 65, if you are around 70, the purpose is to melt your lauric acid. So if I melt, I will have the thermometer on inside in the tip. It should be a mass all the way, and record the temperature after every 30 seconds. After every 30 seconds. After every 30 seconds. You will generate a graph for, all right, you generate a graph for just solvents. Let's say lauric acid. You'll have a graph of temperature versus time on this side. It might just, let me just make up, it might just go like this. It might just go like this, all right? Like that, it will just come down to some plateau. This is the maximum right here. And this is the minimum right here. Minimum. So you can get the freezing point. At some point, it will get the freezing point for the solvent. You'll do the same thing for solution. You'll do the same thing for solution. So if you do it for solution, it might just come back to somewhere there. Freezing point of solution is always low. It should be always low. So let me use a different mark here. If the freezing point for solution is always lower, this is pure solvent, and this is the solution. Solution is always lower than the pure solvent. Our delta will be here. This graph right here, or this portion, is change in freezing point. Change in freezing point. That's why you have to. All right, you have to find the temperature for two trials, trial 1, trial 2. This is the pure lauric acid alone by itself. All right, you may have to only one, but you'll do twice for the solution, lauric acid and benzoic acid. So if I'm done with the solution, direction code for discarding this properly. Let's see. Once you get the change in freezing point from the graph, how will I get that? Is by reading on the y-axis. What is the temperature there? What is the temperature there? If you subtract the two, you should be able to get the change in freezing point. Let me back up on my whiteboard. On my whiteboard, if you look at this one, this equation right here, this is what I'm talking about. You'll find the difference between pure solvent and the solution to give you a positive value, to give you the left side of the reaction of the equation. Remember, what we are using is this one, this equation right here. We have to use the data from the graph to find the left side. That is from the graph. We have the left side. Now, I is 1. Remember, I gave you I. It is 1. Or should I just get rid of this? I is 1. Molar freezing point for lauric acid. If you read the background, what is the molar freezing point? What is, let me ask you, what is Kf of lauric acid? It should be in the background. What is the Kf? I'm just walking you through so that you know how to rearrange the equation. Show me the calculation. Do you have the molar freezing point constant? Do you know the molar freezing point constant for lauric acid? Yes, it should be in the background. Somebody check real quick. We want to finish up this. Let me just minimize this. Where is that? What is the molar freezing point? This is just for H2O, but for lauric acid. What is the Kf for lauric acid? Do you have the molar freezing point for lauric acid? Look, can you see on the screen? Yeah, somebody caught it. Bailey, thank you. Thank you. Look, everybody on the screen, look here. The molar freezing point, the freezing point depression constant, is the same as molar freezing point for lauric acid is 3.90 times 10, not times 10, but 0, 3 significant. And look at the units, yes, degrees per molar, degrees per molar. That is what we need for in this equation right here. You know now this is 3.90, and it is degrees per molar, is degrees per molar, the units. Now we need to rearrange this equation. Remember where we are heading to is to find the number of moles. Look, where we are heading is to find the number of moles. You connect the mass at the top is what you will weigh. This is what you will weigh, but we need to get the denominator. All right, we need to get the denominator in this equation. Sorry about that. How are we going to get the number of moles? It's by rearranging this equation right here. Using this equation, we take everything across the equal sign. Let me make M the subject of the formula. This is how you make M the subject of the formula, by saying right here, okay, molality now, this is where we will get the number of moles, is given by change in freezing point, which you will determine from the graph. You'll get that from the graph, divide by molar freezing point constant for lauric acid, which we just found the value, times I, which I gave you a while back. The I for lauric acid is 1. So we know the numerical value. Let's say this is X molar, or rather molality. Unit for molality is, this is molality, and it is given by the number of what? Number of moles of kg of solvent, all right, in the solution, which means, forget about the other equation. I know there are 2 equations for calculating the number of moles. If I rearrange this equation, number of moles is given by what? Is given by kg of solvent times molality. So I'm just gonna use the molality, the left side on this equation, the left side on my equation here, the left side on my equation here is determined or obtained from this equation 1. Let me call this equation 1. This is equation 2. Equation 2 is used to find the number of moles, And kg of the solvent, it is from what you will weigh from what? What you will weigh from the procedure. The procedure will tell you how many grams of the lauric acid should you use for this round number 1, or trial 1. You plug it in to get the number of moles. With this equation here, with this equation 3 here, you should be able to find the number of moles, which you will plug it in this equation, in this first equation right here. This is what you will need to find the molar mass of your sample, molar mass of your sample. So having said that, you should be able to find the number of, to find the molar mass. Therefore, all right, therefore, right here, therefore, molar mass is given by the mass of sample for each trial. That is what you will weigh out over number of moles, which you'll have to use molality equation. At the outset, there are two equations for finding the number of moles, which I don't want you to get confused and say, you know, or get stuck and say, which one am I going to use? The number of moles is either, this is equation one, number of moles is given by the mass in grams over molar mass. You're not gonna use this today. Number of moles is given by molality times kg of solvent, kg of solvent. I don't want you to get confused and say, which one am I going to use? You'll use equation 2 to find the number of moles, not equation 1. Not equation 1. And then from there, you should be able to find the molar mass, and there is a literature value for the mass of, molar mass of benzoic acid. I think they gave you, yeah, they have it on the barrel right here. Okay, they have it on the barrel. You should be able to find the percent, determine the percent error of your sample. Please read the background on how to find the percent error. Look here, accepted value. Where are you going to get the accepted? Please read on the vial, on the barrel. It is given the literature value. It's even right here. I'm forgetting it. It's right here. Find the percent error. And that will be it. That will be it for this experiment. I expect you to turn in not this week, but by midnight next week. There was a confusion on the due dates. Maybe I got mixed up with other classes. I had to rechange, but I will be giving you until midnight of the subsequent week to turn in the data sheet, and pre-lab you'll be seeing on the assignment folder. You'll be seeing on the assignment folder on Canvas when things are due, all right, post-lab and pre-lab. Other than that, if there is no more question, I want to stop here as far as determination of molar mass of a compound is concerned. I don't want to get into details on the other colligative property. I'll leave it to your lecture instructor to go through the osmotic pressure. There's osmotic pressure, which is also one of the component, one of the colligative properties. If there is no question, I want to end the lecture here today. If there is no question, I want to say thank you. Somebody is asking, Adam, under the assignment for the post-lab and pre-lab, are you in the same files? Oh, I'll check that. No, I'll check that. Maybe I typed the wrong file. I'll check that and fix it due next week. Maybe when I look at 3, I'm gonna fix that as well. I'll recommend, having looked at the procedure, sometimes you may not find enough information, and I want you to be well prepared by the time you are done with the course, that at least you learn something here. You know, for example, what I went through today it will help you in the lecture. It will help you, like, you don't even, whenever you read, it will just be like coming back, like, I understand this, I understand this. This is what I learned in my lecture, like lab lecture or pre-lab lecture. And it will stay forever in your mind. Other than that, you may want to refer to the lecture or internet, any other resources you may have. Other than that, the class is dismissed. I'll see you, or I'll meet with you again next Wednesday, same time. Send me an email, all right? Send me an email if you have any question, and I'll respond within 24 hours. Other than that, thank you, appreciate. Send me an email right now if you haven't received your lab kit, so that I'm aware of what is going on your end. Thank you.